Greetings to everyone. Good morning, all. Today we are going to discuss our fourth unit, that is about semiconductors, polymers, and then we have water. So first coming to semiconductors. So first of all, what are semiconductors? Semiconductors are, everyone knows it, that it is in between conductors and insulators. Right? So semiconductors can be compounds such as gallium arsenide or pure elements such as germanium or silicon. So examples, as I told you, gallium arsenide, germanium and silicon are the most commonly used semiconductors. Out of it, silicon is generally used in electronic circuit fabrication and gallium arsenide is used in solar cells, laser diodes, etc. So we all know that the holes and electrons in semiconductors for flow of current, right? Doping is done, right? That is formation of holes and electrons. So the mobility of electrons is higher than that of the holes. So it is mainly because there are different band structures and scattering mechanics. So I won't go in detail about this holes and electrons. So we have this band theory of semiconductors. So where you know that the band gap of insulator is very high, whereas of conductor is very less, and whereas semiconductors is in between. Right? So next coming to the properties of semiconductors. So it has resistivity, conductivity, temperature coefficient of resistance, and then current flow. Then it acts as an insulator at 0 degree Kelvin. Then on increasing temperature, it works as a conductor. So this may be a common question which is asked, right, generally. So due to their exceptional electrical properties, semiconductors can be modified by doping to make semiconductor devices suitable for energy conversion, switches and amplifiers. So lesser power losses is there. And then semiconductors are smaller in size and possess less weight. So their resistivity is higher than conductors but lesser than insulators. So the resistance of semiconductor materials decreases with increase in temperature and vice versa. Now types of semiconductors. So in these types of semiconductors, we have intrinsic semiconductor and extrinsic semiconductor. So intrinsic semiconductor, we have pure form of germanium and silicon. Whereas extrinsic semiconductors, we have N-type and P-type. So N-type is pentavalent impurities are added, it is phosphorus, arsenic, tritium, etc. And P-type, trivalent impurities such as gallium, boron, indium, aluminum are added. So you can take this example of intrinsic semiconductors where there is a broken bond between this silicon and silicon, okay, and then it has been inserted with an electron. So holes and electrons are formed. Then this is the band energy band diagram of intrinsic semiconductor. So you can see here. Right. Then coming to extrinsic semiconductors, so it is N-type and P-type, right? Doping is done. So here with lead and here with boron. So here donor impurity contributes free electrons in N-type, whereas in P-type, accepted impurity creates a hole. So because of this hole and electrons formation, it is able to conduct electricity. Then coming to N-type semiconductor and P-type, you can have these N-type as donors and P-types as acceptors. Okay. And differences are intrinsic semiconductor is a pure semiconductor, extrinsic is impure semiconductor. Then intrinsic density of electrons is equal to the density of the holes. Whereas extrinsic semiconductor density of electrons is not equal to density of holes. Then electrical conductivity is low and here electrical conductivity is high in extrinsic. So it depends on temperature only intrinsic, whereas extrinsic depends on temperature as well as the amount of impurity which is going to be added. Okay. In intrinsic, there are no impurities, whereas in extrinsic, trivalent impurities and pentavalent impurities are added. Okay. Then coming to the applications of semiconductors. So these semiconductors we use in daily life, right? In all electronic devices. So temperature sensors are made with semiconductor devices. Then they are used in 3D printing machines. Then used in microchips and self-driving cars. Used in calculators, solar plates, computers, and other electronic devices. Then transistor and MOSFET used as switch in electrical circuits are manufactured using the semiconductors. So we have this importance of semiconductors because they are highly portable due to their smaller size and they require less input power. Then semiconductor devices are shockproof. Then they have a longer lifespan and they are noise free while operating. So because of these applications and uh, importances, semiconductors are used. Okay. Now we'll go for another topic, that is preparation of semiconductors by using zone refining technique. So this preparation or manufacturing of semiconductors is done by three methods. First one is zone refining, second is Saralski crystal pulling technique, and third one is doping. So first we study about zone refining. Okay, so ultra purification by zone refining. So this technique is used to obtain ultra pure elements based on the principle that impurities are more soluble in the melt than in the soluble state, solid state. So this is the main principle of zone refining technique, that impurities are more soluble in the melt than in the solid state. That means when it is in solid state, there are no impurities. Whereas if you just melt it, so that melt has impurities present in it. Okay. So this is the main principle of zone refining technique. That is that impurities are more soluble in the melt than in the solid state. Okay. Now, this involves melting a narrow zone or region of a long ingot of the semiconductor material to be processed. Suppose we want to prepare a germanium or silicon rod, pure ones. Okay. Then we go for the zone refining technique. So what we do here is we just take a long rod of it, okay, and then we start melting that. Okay, so the molten zone is slowly moved with a predetermined speed by a traveling heater gradually along the length of the ingot in one direction. So I'll just do a what to see. I'll just suppose this is our what to say, germanium rod or silicon rod. Okay. Now what I do is to this rod, I put a circular heater. Okay. And suppose this is the circular heater for me, and I'm moving this circular heater along this rod. Okay. Along this rod, I am moving the circular heater. So what is happening? When I am moving this, this becomes the melt part. Okay. And this becomes the solidified part. So where are the impurities present now? In the melt part. Okay. The solid is not having any impurities. It is very pure in nature now. Okay. So similarly, you just move this circular heater around the rod and come to this side. Okay. So what happens is this all becomes solidified and the melt part is left behind here. So we just cut this and use this rod now as a pure germanium or silicon rod. Okay. I think you people have been understood. Okay. So polycrystalline mass of elements. So we prepare a polycrystalline germanium rod. So it is not a single crystal, it is polycrystalline. So polycrystalline mass of elements purified in the above process are pressed into a rod and fixed vertically in a furnace provided with a circular radio frequency heater. So the heat is focused onto a small portion of the rod while it rotates, and the hot molten zone is made to travel slowly with a predetermined rate from top to bottom by allowing the heater to travel so that the impurities also move along the molten zone. Okay. So by repeating this process multiple times, so many times they just move the circular heater around the rod. Okay. Impurities get concentrated at the bottom portion, which can be cut and removed from the pure part. Now the purity reaches to, see here, 99.9999%. So the zone refiner can be set horizontally also. So if you see the diagram, then you have this, yeah. So this is the base metal which we have taken, okay, and we are providing this with a circular heater, right? Now this is our moving direction. So we are moving in this direction, particular direction. Okay. So we are moving like this. So what is happening as we are moving like this part is getting solid, right? So this is forming, sorry, I'm not able to write clearly. Okay. So this is becoming solid part which is not having any impurities present in it. Okay. So then this is a melt part. So this melt part is having impurities now. Okay. So likewise, what happens? They get this to the corner. Okay. And then they cut. Suppose this melt is now in this part. Okay. So till here the rod is cut, and this will be around 99.99% pure. Okay. So what they do is they do this process or repeat this process many times so that we get around this percent pure, right, germanium rod. Clear? So this is the process of zone refining technique. Okay. So today's class we have studied about the introduction of semiconductors, that is what is a semiconductor, then what are the properties of semiconductors, then what are the applications of semiconductors, what is the importance of semiconductors, then its types of semiconductors, that is intrinsic, extrinsic. In extrinsic again we have p-type and n-type. Then we have this preparation of semiconductor by zone refining process. So in zone refining process, we develop polycrystalline material, and the main principle is that the impurities are more soluble in the melt than in the solid state. And we get around 99.9999% pure metal. Okay, all of you. So in next class, we will be discussing about other two methods of preparation of semiconductors, that is Soralsky crystal pulling technique and